Hi everyone. Today we'll have a lesson on estimating with finite sums. And a couple of things I want to say first. I know that the last lesson that we had was very long, and this lesson will be a little shorter. So this lesson and the next one will be a little on the shorter side after that gigantic section we had about antiderivatives. So one thing I want to say is that this lesson and the next one are going to seem like we're talking about a different topic. It's going to seem like we're not talking about antiderivatives. But antiderivatives are going to come back a lesson after that. And we're going to see how all of these things go together. The things that we talked about last time and the things we're talking about this time. They seem different, but trust me, they're going to click together soon. All right, so let's get started. So, like with a lot of topics, I want to start this topic with a question. A lot of times I like to start with a question to kind of show us the motivation of what is this topic going to be all about. So, suppose we have a continuous function y equals f of x defined on an interval from a to b. I'll draw a picture of some kind of continuous function on some kind of interval from a to b, and then I'll ask a question about it. There are lots of functions that fit this description, and I'm just going to make one up. Let's just say it's some kind of curve, goes like that maybe, and stops. The reason it starts in one place and stops in another is because we said it's defined on a domain from A to B. So there's some number A and some number B that we're using as the interval. So this curve is y equals f of x. And the question that I want to ask is, what is the area under the curve? What is the area under this curve? So I think I'm going to add to this picture. Now that I've posed the question, I'm going to show you what does the area under the curve look like? Well, we could shade it in. We could say that the area under the curve, I guess if you say everything under this curve, well, it keeps going down and down and down forever, right? So when we ask this question, what we really mean is what's the area under the curve but above the x-axis? And you see we're creating this region here. It's everything below the curve but above the x-axis. We get this weird shape with a curved surface on the top. I guess you could say that the left edge of this shape is sort of a straight line segment. The bottom is kind of a straight line segment, and the right side is a straight line segment, but the top is curved, and that makes it difficult to figure out the area. Now, I have a more fundamental question. A more fundamental question. What is area? What do we mean by the word area? Have we defined it? Have you ever seen a definition of area in a math class? I think that we have an intuitive idea of what it means. And if you asked me to give a definition, I don't know, I might say it's something like the amount of space that the region occupies. How much space does this region occupy in the XY plane? What portion of the XY plane is this? And, we would measure it in square units. I want to say that we know exactly what area means for rectangles, right? The area of a rectangle would be the width times the height, or length times width, or whatever you want to call it, one side times the other. That's the area of a rectangle. I think we also know the area of triangles, and I think we know the area of circles. But what about like a weird curved region like this? What about curved regions? In particular, curved regions that are sort of traced out by some kind of continuous function. It's tricky, right? I guess you could get out like a ruler and you could try to measure out the square units, but the curve is going to make it difficult. So here's an idea. We can estimate. We can estimate it using rectangles. Now, this shaded in region up above is not a rectangle, but I mentioned that 3 of the sides were straight line segments. It's just the top that's not. So maybe what we could do is we could try to chop this up into rectangles, and since we know exactly what the area of a rectangle is, it would help us approximate or estimate the area of this region. Now, above, what I drew was just kind of a generic make-believe continuous function, but let's do an example with a specific function. And we are going to estimate the area under the function f of x equals x squared on the interval from 0 to 1. And we're going to talk about this example for a while. This is actually going to be our main example of this lesson. And I'll show you how we can use rectangles to help us answer this. First of all, let's draw a picture. All right, we know what this function looks like. It's a parabola. But on this particular interval, we're kind of restricting the domain to just be from 0 to 1. So it's not the entire parabola. It's just the parabola going from 0 to 1. The sort of stuff that's in quadrant 1 here. And I guess I know that 1 squared is 1, so I know it passes through the point 1 comma 1. And we have part of a parabola. Like that. And I'm just going to stop there. My y-axis, my x-axis. So the area under this curve would be this region. Definitely not a rectangle. It's also not a triangle or any other kind of easy shape to work with. Can we figure out the area of this weird shape? I guess you could say that right away, I know that the answer is less than 1. Less than 1 square unit, because 1 square unit would be a 1 by 1 square. And we have a lot less than that shaded in. In fact, I think we could also make an argument based on the picture that this area has to be less than 1/2. Less than 1/2 of a square unit. Because if I just drew a straight line connecting these two dots and made a triangle, that triangle would have an area of 1/2. But this shaded region looks smaller than that. So I'm going to say, note, the answer is less than 0.5. All right, maybe it's around 0.3 or 0.4. But we don't know exactly what it is yet. But we could start by saying that the area is somewhere between 0 and 0.5. So I guess I'm calling the area A. I'll put a big, how about this? We'll put a big A in this region. The area that we're looking for is called A. We have a lot more to discuss, but I'm going to circle this. The problem said to estimate the area, and I'm going to say this is kind of our first estimate. We're kind of saying the area is somewhere between 0 and 0.5, and now we're going to try to narrow it down a little bit more. Is it between 0.1 and 0.4 maybe? You know, let's try to figure this out. Now, I said something about using rectangles. So here is the basic idea. We are going to think of dividing this region into vertical strips. I'm going to wind up drawing a few pictures of this same region but that's okay. It's a pretty easy curve for us to work with. So here's 1, here's 0, here's 1. Let's draw the curve again. All right. I'm going to divide it into 4 vertical strips. Let's just chop it down the middle and just try to make 4 vertical strips that have the same width. There's a fourth of it, another fourth of it, another fourth of it, and another fourth of it. Actually, if we have these all having the same width, the width would be 1/4. So I could mark this 1/4, 1/2, 3/4. And we already have the 0 and the 1 labeled. Do you see that if we could figure out the area of each of those vertical strips, we could just add them all together and that would give us A? So we're taking the area and dividing it into 4 kind of sub-regions. Well, the next step that we do is we turn the strips into rectangles. So for this, I'm actually just going to draw the picture again. You could draw a separate picture, or you could just draw on top of the old one if you want. But how do we turn these into rectangles? They're not rectangles. They're not exactly rectangles. They're not exactly triangles or any other shape that are easy to work with, but here's the idea. Take that picture that we had before. 1/4, 1/2, 3/4, and over here is 0. Okay, each one of these, let's like focus on the third vertical strip here, like this one that I'm pointing at. What's preventing this from being a rectangle? It's the top, right? Because the left side is flat, the right side is flat, and the bottom is flat. Those are just line segments. It's the top that's curved. So if I wanted to somehow make a rectangle based on this, I need to do something about the top. Let's look at where these vertical strips touch the curve. I'm going to shade these in as dots. There's a dot here, and a dot here. That's where the vertical strips touch the curve. One way that I could turn these vertical strips into rectangles is start at the upper right and just kind of make sort of a staircase where I'm connecting these dots, basically. See what I did? So the third vertical strip has become kind of the third rectangle, and the rectangle goes to a height of this dot. Well, that dot is where the function is when x is 3/4. I'm going to shade in these 4 rectangles. Now, we could figure out the area of these 4 rectangles. This is not exactly the answer that we're looking for, right? Because up above, I drew the original picture. We're looking for this area A. And this new picture that I drew, if we figure out the area of these 4 rectangles, I think it's going to add up to be too much. It's going to be larger than what A is. But it's a starting point. It's basically, we're trying to estimate that area A, and this is going to provide one estimate of it. So I'm going to say the area of this shaded region equals the sum of areas of 4 rectangles. This section was called estimating with finite sums. So here is a sum. It's a finite sum because there's just a sum of 4 things, and 4 is a finite number. And we're going to use it to estimate area. So that's why it's estimating with sums. So we have a name for this area. I'm not going to call it A because it's not exactly A. I'm going to call it R4. Now, the 4 is because there are 4 rectangles. The R is, well, I guess I'll tell you now. I was going to wait to tell you, but there are 2 ways that we could have turned this into rectangles. We're going to wind up doing both of them. One is going to be R, and one of them is going to be L, and they represent the right and left. The reason is because when I made these rectangles, I started at the upper right, and I kind of chopped this up into rectangles. And every one of these rectangles touches the curve at its upper right. Like the 3rd rectangle, where does it touch? What corner of the rectangle touches the curve? It's the upper right. What corner of this rectangle touches the curve? The upper right. So we call these the right rectangles, and we call this R4. Now, what's the area of these? What's the area of each of these? Length times height, right? Or width times height. So the width of each of these looks like it's 1/4. So 1/4 times the height is the area of the first rectangle. 1/4 times... What's the height of the first rectangle? Well, we don't know it exactly as a number yet, do we? But look at this. When x is 1/4, that's where the height of the rectangle is. When x is 1/4, how high is the function there? F of 1/4. That's the height. So this right here is the area of the first rectangle. Width times height. The next rectangle has a width of 1/4 and a height of f of 1/2. The third rectangle has a width of 1/4 and a height of f of 3/4. And the final rectangle has a width of 1/4 and a height of f of 1, because that's how high up this is, f of 1. Remember, the curve that we're dealing with here is f of x equals x squared. So I could evaluate this. 1/4 times 1/4 squared. This is going to give us just a number, which is good. The reason why I'm squaring these is because the function that we're working with is f of x equals x squared. So that's what you do. F of 1/4 is 1/4 squared. If the function that I was looking at was a different function, like sine x, or e to the x, or x to the third, we would do something else here. But I'm squaring because that's the function that the problem gave us. All right, so I'm going to tell you that I worked all this out. You can do 1/4 squared, 1/2 squared, and all that. I worked this all out, found a common denominator, and I wound up getting 15/32 as the area of this shaded region. I also found this as a decimal to be 0.46875. That's exactly what this fraction equals. I said before we actually did all this, I said that this shaded region looked like it was going to be too much area. Like the actual area A that we're looking for is smaller than this, right? Because these rectangles have all these extra little pieces up here. So I'm going to say that this is an overestimate for A. It's too much. But what we could say then is A, the actual area, must be smaller than this. So we could say that A is somewhere between 0 and 0.46875. And I'm going to circle this just like I circled that earlier statement. We still have more work to do. But do you see, we're trying to narrow this down. We're trying to figure out the area A is between something and something, and maybe we can do better with this left-hand number. And close this in and get an estimate for the actual area. So R4 is based on 4 rectangles with right endpoints touching the curve. But I mentioned that there is also another way that we could have turned the strips into rectangles. I'll show you that. When we had the 4 vertical strips, picture looked something like this. There's 1/4, 1/2, 3/4, 1. Here's 0, height of 1. All right, that's the 4 vertical strips. What if instead of starting at the upper right and making that kind of staircase and each rectangle using the upper right corner, what if we used the left? What if I start at the lower left? Actually, let's draw a dot at each of these. And what I'm going to do, we could draw a dot at the top one too. What I'm going to do is I'm going to draw rectangles in a way so that the upper left corner of each rectangle touches the curve. The upper left corner of each rectangle touches the curve. I guess my first rectangle is just kind of down here. There's kind of like nothing there. And I'm going to shade in these rectangles. Well, this is another way that we could have turned the vertical strips into rectangles. I guess rectangle number 1 looks like it doesn't have any height at all. This tiny little thing here. If we figured out the area of this shaded region, what's that going to be? Area of this shaded region. Well, I'm going to call it L4. It's still made up from 4 rectangles, but this time we have the upper left endpoints touching the curve. Again, we could do the area of each rectangle added together. So the area of the first rectangle, the second rectangle, the third, and the fourth, they still have a width of 1/4. So what's the height of this first rectangle? It's 0, isn't it? It's not really a rectangle at all, but I'm including it anyway, just for completeness sake. How do I know it's 0? I guess it's this, what's the height of the curve at this spot? We could think of it as f of 0. It's going to wind up being 0. The second rectangle has a width of 1/4 and a height of, how high up is this dot? That dot is at a height of f of 1/4. And then the third rectangle, width of 1/4 and a height of f of 1/2. And the fourth one has a width of 1/4 and a height of f of 3/4. This almost looks like what we did above, but not exactly the same. It's going to get us a different number. If you work this all out, I mean, you basically just have to square these things. So that's the function we're dealing with. Kind of seems like we could pull the 1/4 all the way out front if we wanted, factor out a 1/4, because that appears everywhere. All right. We square these fractions. I mean, like I said, that first one is just a 0. This winds up equaling, and you can figure this out. You can square fractions, and you can find common denominators and all that. So I'm skipping some of that little arithmetic, but this is 7/32. It's a lot. It makes sense that it's a lot smaller than the other one. I found this as a decimal to be 0.21875. Looking at this picture, I think this is definitely an underestimate for A. Remember what A is up here? This is the actual area under the curve, the actual area of the region that we're looking for. This region that we just did is too small. It's missing, you can see it's missing some part of the region. So this 0.2 something is an underestimate for A, which means that the true area A is greater than this. So combining that with what we said above, we could definitively say that 0.21875 is less than A, and A is less than 0.46875. We're trying to estimate A, and we've figured out that it must be somewhere between these two numbers. Do you think, is it possible that maybe the actual area is just right in the middle of these two? Like, this is 0.2 something, this is 0.4 something. Maybe the actual area is 0.3 something. Maybe it's like the average of these two to be exactly in the middle. So here's an idea. Let's do the average of L4 and R4. This suggests that the area is approximately equal to, we don't know if it's exactly this, but I found the average of these two decimals was 0.34375. I'm going to put a question mark next to it because we don't know how close that is. I'm going to circle it anyway. If you ask me for an estimate of the area, based on what we've said so far, this is probably my best guess so far, because I know it's between these two. So maybe I say it's the average of the two of them. Maybe. We still have more work to do, though. All right, so we're going to approach this in another way. I'll just give you a chance to get all of this. Okay, so let's move the page up. And I'll show you another idea. So we've tried chopping up the region into 4 vertical strips and then turning them into 4 rectangles, either with using the upper right endpoints or the upper left endpoints, basically which part of the rectangle touches the curve. So another idea is called the midpoint rule. And this is where we're going to chop the region up into rectangles. It's still going to be 4 vertical strips. We could actually go back to that exact same picture of 4 vertical strips. This is the region, and they still kind of touch the x-axis at 1/4, 1/2, 3/4. But this time, instead of drawing a dot where each of those vertical strips touches the curve, I'm going to focus on the midpoints of each of these vertical strips. So what is halfway in between these two? It would be here, 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 and here. Okay, so they're basically at these midpoints. Maybe I can zoom in on this. There we go. So these midpoints have these dots over them. And then I'm going to use those to create the tops of the rectangles. So a top of a rectangle here, 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 and here. What do you think about these rectangles? What if we shade in these, and what if we find out the area of all 4 of these rectangles? Is this going to be... Do you think this is going to be an overestimate, or do you think this is going to be an underestimate for A? Well, let's see what it looks like when it's all shaded in. Seems like maybe this is a nicer way to do it instead of those left endpoints or right endpoints. When we first did the right endpoints, we had something that was definitely an overestimate. The left endpoints were definitely an underestimate. This one, it's kind of harder to tell, right? Because this seems like it's accumulating some extra area that's above the curve, here, 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 and here. But it's also missing little pieces of area that are under the curve. So maybe that kind of balances out, and maybe overall this will be a pretty good estimate. In order to work with this one, though, we have to figure out where are these endpoints. Well, I said they were halfway between each thing, so what's halfway between 0 and 1/4? It would be 1/8. And what's halfway in between 1/4 and 1/2? 3/8. And halfway between 1/2 and 3/4 is 5/8. And halfway between 3/4 and 1 is 7/8. All right, so those are the numbers that we're going to be working with. That's where those dots are. Those are the x coordinates of those dots. And those dots are telling us the top of the rectangle. So I'll zoom out again. And we called the other ones L4 and R4. We're going to call this one M4. It's still 4 vertical strips. So M4 is the sum of these 4 areas, of these 4 rectangles. Each of these rectangles still has an area, or still has a width of 1/4. And it's still 1/4 times f of something plus 1/4 of f of something. You know, width times height, width times height. And the height of each of these 4 rectangles is going to be f of 1/8, f of 3/8, and so on. So you see, all of these methods that we've been doing, they all look similar, but they get us different answers. And we could do this by hand. You know, we could square that, square each of these. What are we going to get? A denominator of 64. All right, so I did this already. I worked this all out. I found that this one is 0.328125. I think that was something over 64. So, does this suggest that the actual area of the region is approximately equal to 0.328125? I'm going to put a question mark next to it because we don't know how close that is to the true area under the curve. Seems like it might be a good estimate, though. So I want to show you our 2 latest estimates. We can fit them both on the screen. Above, we found L4, we found R4. We said the area has to be in between them. So the idea was, what if we take their average? And we got 0.34 something. And then we said, well, what if we try the midpoint idea? And that got us this. So then there's a question of like, well, is the true area of the region one of these? Or is it pretty close to one of these? Should we average these two? It's not really clear, right? We don't know exactly. But another thing that we could think about is, why have we been dividing this into 4 vertical strips? What if we did more than 4? Can you imagine if we had divided this into 8 vertical strips or 10 vertical strips? They would be small, thinner rectangles, and maybe they would kind of line up with the curve a little bit closer. And that's true. The more rectangles we use, the better the estimate is going to be. It's still just going to be an estimate, but more rectangles is going to be a better estimate. The reason why we've used 4 is because 4 is pretty easy to work with. It's pretty easy to illustrate. And in this class, you'll probably be asked to work with maybe 4 rectangles or 6 rectangles, somewhere in that neighborhood. I don't know. Maybe you would get asked to do 8 rectangles at some point. But the more there are, the more things we have to add up, so it becomes more work for us. Now, let's take a step back and speak more generally about this type of problem. All right. This whole time, we've been working with the function f of x equals x squared. We had a certain interval that was given, an area we've been trying to estimate. But this principle could also apply to other functions and other intervals, so we want to be more broad here. I'm going to say that the width of each rectangle is, you know how I've been saying the width of all of these is 1/4? Do you think that it was 1/4 because we did 4 vertical strips? Well, that's part of the reason. The other reason why the width was 1/4 is because we had 4 vertical strips and we were only looking from 0 to 1. So it seems like, remember how we called this A and we called this B at the beginning of the lesson? So it seems like A and B and the number of rectangles are what determine the width of each rectangle. So let's say we're going to call this delta x, and the formula for it is b minus a over n, where the interval from a to b is partitioned into n vertical strips of equal width. Does that make sense? Yeah, look, it works with the example we did earlier. We'd have 1 minus 0 over 4. So the width of all of these was 1/4. I used the word partition. I want to talk about that a little bit more. So these divide the interval from a to b into n subintervals. I think I might have used that word earlier. But yeah, we're dividing it into n subintervals. And we could give these names. We could say it's sort of x0 to x1, x1 to x2, x2 to x3. We're being general here, so we're supposing there are n of them, and we don't know what n is. Maybe it's 4, maybe it's something larger. The final interval would be xn minus 1 to xn. I guess I'll say where x sub 0 is a and x sub n is b. You can see that, right? Because that's the beginning. The first interval starts with a, and the last interval ends with b. So these sums that we've been doing, all of these ones we've done, L4, R4, and M4, they've all looked similar. They've all had a similar structure. It's like width times f of something, width times f of something. And these sums are called Riemann sums. So this is named after a mathematician. The name is Riemann. Riemann sums. Now, I said a moment ago that we would get better results if we used more rectangles. So, better results if we use, let's say 8. Let's say 8 rectangles. We would get a better estimate of the true area under the curve. And we're not going to go through all of that work right now, but I am going to draw a picture of it. So I'll draw 2 pictures of it, in fact. So I'm kind of going back to that example of f of x equals x squared, the interval from 0 to 1. It's part of a parabola. You might be asked to do some problems that do other functions. All right, so what would this look like if we tried to slice this up into 8 vertical strips of equal width? Look like that. I'm going to do it again over here. So you can see that each one of these would have a width of 1/8. You could also get that from that little formula. B minus A over N would tell you that the width of each one of these, the delta X, would be 1/8. So how should we chop these up into rectangles? Well, let's do the R and the L version of it. So we would take maybe the right, upper right endpoints and make them touch the curve and make those the tops of the rectangle. So it would look like this. So this region of all these rectangles added together is one way that we could do it. And if we did this, this would be called R8. And I think if you compare this with the picture that we drew for R4, I think that this is looking like it's a better estimate. It's still an overestimate of A, but it seems like it kind of stays closer to the curve. And same thing is going to happen for L4. So I'll do L8. So I'll do L8 over here. So I think L8 is going to look better than L4 did as far as sort of lining up with the curve, staying closer to it, and giving us a closer estimate to the true area A. Maybe we could do L8 and R8 and then take the average of them. Since one of them is an overestimate and one of them is an underestimate, take the average of them, right? So I'm going to tell you what happens if we had done that, because I worked it out. And the better results that we get are that it tells us that the area is between 0.2734 and 0.3984. So like we did with L4 and R4, I'm saying the area has to be between them. And if you take the average of these, if you say maybe the area is approximately equal to the average of these, it is 0.3359. And I claim that this, well, I'll put a question mark because I did that with the other ones, but I claim that this is the best estimate that we've gotten so far today for the true area under that curve for that interval. So I'm going to move the pictures away. How about this? So, okay, we did 4 rectangles. We get some numbers. If you do 8 rectangles, you get some numbers that I say are better. What if we use 1,000 rectangles? What if we did L1000 and R1000? Those would line up really closely, right? Can you imagine that? Can you look at the L8 and R8 and imagine if there were 1,000 rectangles? They'd be incredibly thin, and there'd be 1,000 of them in this picture, so it would be hard to even draw them. But the tops of the rectangles, like, they would line up really, really closely with the curve. It would look almost indistinguishable from the curve, and it would probably get us a really, really good estimate of the area. Maybe we could even do the midpoint rule and do like M1000, and we would get a good approximation there also. Well, you might be guessing where we're headed with this. What if we use the limit as n goes to infinity? Let the number of rectangles approach infinity. So this is what we're going to be doing soon. We're not doing it yet in this section, but I do want you to start thinking about it. The number of rectangles approaching infinity. What would their width be? And that's kind of weird, right? The width would get thinner and thinner and thinner. So I guess the width of each rectangle would be approaching 0. But it wouldn't really equal 0. It would just be approaching 0. I'm going to tell you the answer. that we would get. The result that we would get would actually be the exact area under the curve. And I'm actually putting an equal sign here. This is the first time I've put an equal sign. And you would get an answer of 1/3. And that is the true area under that curve for that interval. So all of the numbers that we've said so far today have been an approximation of this. That last one that we got, 0.3359, it's approximately 1/3. Even the ones we got earlier, 0.328, 0.34 something, they were all pretty close, pretty close. Even with 4 rectangles, it seemed like we got pretty close. Now, I haven't told you how I got exactly 1/3, but I hope that some of these numbers suggest to you that 1/3 seems plausible. We're going to be doing this soon, the limit as n goes to infinity. But I'll remind you that the title of this lesson was Estimating with Finite Sums. And maybe now you can see why the title was called that. It's because pretty soon in upcoming lessons, we're going to have an infinite sum. Add up an infinite number of rectangles. How do you even do that? So we have to talk about that soon. But this lesson was about using 4 rectangles, 8 rectangles, just some small finite number. You're adding them, so we are estimating with finite sums. So, now you know where we're headed with this, and this is really where the calculus part comes in, because it might seem like we didn't really do much calculus today. We didn't really do any limits or derivatives or antiderivatives. Or did we? Actually, you're going to see in an upcoming lesson how this is related to antiderivatives, believe it or not. So we spent a lot of time on one example. We spent most of this discussing... Here, I'll go back to what the question was. We spent most of this lesson focused on estimating the area under this function for this interval, and this was like the thing we were trying to approximate. I'm telling you now that this is exactly 1/3. But you could be asked to do this for a different function or a different interval. And I guess a problem that you might see in homework or a quiz or an exam or something for this section, it would probably tell you how many rectangles to use. And it would probably tell you to use either left endpoints or right endpoints or midpoints. So you know that we're doing either like L4 or R4 or M4. And you might draw a picture like this to figure out where these points are. You would need to figure out the width of each rectangle. You could figure out the width of each rectangle by using the picture or that little formula we had. Right here. Maybe I didn't emphasize this enough. Let's put a box around it. You could use that to figure out the width of each rectangle. The width of each rectangle, of course, showed up in our computations for L4 and R4 and M4. If you were asked to do this with 6 rectangles, then n would be 6. B and A are going to come from that original interval you're given. So I think you'd be ready to do this for some other functions besides the one we did. All right, so that was estimating with finite sums, and you can see, what were we estimating? We were estimating the area under the curve. And it's not such a simple thing, right? Area of a weird curved shape is kind of a tricky question. And it turns out that to get the exact area, we're going to have to do the limit as n goes to infinity, and that's coming up in future lessons. But for now, we were able to estimate it using like n equals 4, and something like that gets you a pretty good estimate, which could be written as a fraction or as a decimal. So what else have I got to say? I think I mentioned, and I'll say it again, that this topic might seem like it has nothing to do with the previous lesson, right? It seems like, what's going on? Why are these two lessons side by side? But just bear with me, and it will all eventually click together, and we're going to see that all of this fits into a big picture, and it's all kind of part of the same idea. We just have to get there. Okay, so that's going to be it, and I'll see you next time.